Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Polina Levchenko. Polina joined the Institute for Information Transmissions Problems of the Russian Academy of Sciences in 2021. She is currently an intern researcher at the Wireless Networks Lab of ITPRAS and is on her way to receive a bachelor degree this year. Today she will present us the results of her work about performance comparison of NB5 Sigfox and LoRaWAN technologies. Polina, the floor is yours.
Good afternoon, everybody. The topic of today's seminar is the performance comparison of NB5 Sigfox and LoRaWAN. If you have any questions, I'm happy to answer them at the end of the presentation. So let's begin. The Internet of Things is rapidly evolving. According to recent studies, 27 billion of devices will be connected to the Internet of Things by 2025, many of which will require low energy consumption and a wide area of connectivity. Low power wide area networks, LPWAN for short, satisfy these requirements and serve large numbers of devices over long distances with relatively small energy consumption. LPWAN technologies have many applications, which include smart buildings, smart metering, agriculture, smart cities. The most popular LPWAN technology operating in the unlicensed frequency band is LoRaWAN. Its networks have been deployed in more than 170 countries. Another popular LPWAN technology is Sigfox, which is used in more than 70 countries. NB5 is a rather new LPWAN technology. However, in a short time, NB5 networks have been deployed in several countries. Although NB5 is defined for similar scenarios as LoRaWAN and Sigfox, it uses different approaches. By now, no detailed comparisons of NB5, Sigfox, and LoRaWAN exist in scientific literature, except for a few surveys that compare their nominal operational parameters, such as modulation, coding schemes, and corresponding bit rates. However, the performance at the upper layers for large networks significantly depends on many factors, including the overhead induced by packet headers and transmission protocols, inter-packet gaps, channel access procedure, and the approaches to resolve collisions during random access. As a result, it is not clear which technology shall be selected for a particular use case. Therefore, the goal of this research is to compare the performance of NB5, Sigfox, and LoRaWAN in various scenarios in order to determine which technology to use under which condition. Let's turn to related works. LP1 technologies have attracted much attention in the scientific literature. Some works evaluate the performance of a single LP1 technologies using simulation, like, for example, works 3, 4, and 5. Results of such works, however, are not applicable to the current research, since NB5, LoRaWAN, and Sigfox are studied in different scenarios. Some works compare the most popular technologies, Sigfox and LoRaWAN, like works 6 through 9. However, the results obtained in these works cannot be used to compare the technologies, because the results either cannot be applied to NB5 because of its features, or the scenarios do not represent a typical sensor network. Papers 1 and 2 compare all three technologies. However, the authors of these papers compare nominal characteristics of these technologies, such as the maximal data rate, transmission range, number of devices connected to a base station, while the real network performance requires more detailed study in various scenarios. Let's move on to an overview of NB5, Sigfox, and LoRaWAN. This section is divided into 4 parts: network architecture, modulation, transmission parameters, receiver sensitivity, operation modes, and channel access. Let's start with network architecture. A typical NB5, Sigfox, or LoRaWAN network has a stars of stars topology and consists of N devices or sensors, base stations, and the server. In the considered LPWAN technologies, base stations are connected with the server via a broadband link, or the server may be implemented on the base station. Sensors communicate with the server via base stations using wireless NB5 Sigfox or LoRaWAN links, while base stations act as transparent retransmitters between the sensors and the server. Sensors are not associated with a single base station, so any base station that receives a frame from a sensor redirects it to the server, while in the reverse direction, the server chooses which base station transmits a frame to the sensor. Moving on now to modulation. NB5 and Sigfox sensors communicate with the base station using differential binary phase shift keying, DBPSK for short, in the uplink. In the downlink, NB5 base stations use DBPSK or binary phase shift keying, BPSK. Sigfox base station use Gaussian phase shift keying in the downlink. LoRaWAN sensors communicate with base stations using the LoRa technology, which is based on the chirp spread spectrum modulation. In LoRa, the signal continuously varies within a window around the central frequency. The frequency starts with 1 of 2 to the power of SF values within the window. SF stands for the spreading factor, which defines the symbol duration and the number of bits per symbol. Then the frequency increases until it reaches the top value, drops to the minimal value, and continues growing until it reaches the initial value. The key feature of the LoRa modulation is that frames transmitted with different spreading factors can be received and decoded simultaneously. Let's move on to the transmission parameters. In NB5, frames can be transmitted at 4 different bit rates: 50, 400, 3200, or 25,600 bits per second. In Sigfox, frames can be transmitted with 2 different bit rates, 100 and 600 bits per second. The rate affects the frame duration and the bandwidth used for the frame transmission, like shown on the picture. The lower is the rate, the higher can be the transmission range, meaning the maximal distance between the transmitter and the receiver at which the communication is still reliable. LoRaWAN sensors can transmit frames with 6 different spreading factors, from 7 to 12. This results in 6 different bit rates, varying from 250 bits per second and up to 5,470 bits per second. Let's now turn to the receiver sensitivity. NB5 specification defines an equation shown on the slide to calculate the receiver sensitivity. The receiver sensitivity is calculated using the Boltzmann constant, temperature, signal frequency band, the input noise, and signal to noise ratio corresponding to the given bit error rate. The specification also provides the typical values for input noise and bit error rate and signal to noise ratio corresponding to the given bit error rate. Sigfox and LoRaWAN specification just define the receiver sensitivity. Let's move on to operation modes in NB5. NB5 sensors can operate in 3 modes. By default, the sensors operate in the discontinuous RX mode. In this mode, the sensors transmit data if needed and listen to the downlink channel for a short period of time after the end of their transmission. The second mode, called No RX, supports only one-way communications from sensors to base station. In this mode, the sensors transmit data if needed. Otherwise, they stay in the sleep state with their radio switched off. In the last mode, called continuous RX mode, the sensors always listen to the channel and can transmit and receive data at any time. Most of the devices in sensor networks are battery powered and therefore do not use this mode. Let us consider the transmission procedure of an NB5 sensor working in the DRX mode, illustrated on the slide. TB seconds after the start of the frame transmission, the sensor starts listening to the downlink channel for TL seconds. If in this time interval the sensor does not receive an acknowledgement, it retransmits a frame after a random backoff time uniformly distributed within the retry window T R&D. The sensor retransmits the frame until it receives an acknowledgement or exceeds a configurable retry limit. Moving on to the operation modes in Sigfox. To transmit the frame, Sigfox sensors can use one of the two modes, U procedure or B procedure. With the U procedure, sensors send their frames in the uplink with no onward downlink frame. With B procedure, sensor requests a response from the base station to their uplink frame. And after the sensor receives the downlink frame, it has to confirm the reception. The Sigfox sensors also may send a frame once or 3 times, which improves transmission reliability. Sigfox rules allow for creating and transmitting either one, called a single frame procedure, or 3 frames with identical payload, called multiple frame procedure. Turning to the transmission procedure for Sigfox sensor operating in the U procedure. The first transmission attempt occurs at a random frequency within the uplink channel. If the sensor transmits the frame only once, meaning that the sensor operates in the single frame procedure, it waits for at least 10 milliseconds after the transmission before it can initiate a new procedure. Otherwise, if the sensor operates in the multiple frame procedure, then it repeats the transmission twice at random central frequencies, each time waiting for TU seconds after the previous transmission. The sensor completes the transmission procedure TP seconds after the last transmission. Let's proceed to the operation modes in LoRaWAN. A LoRaWAN operator divides the available spectrum into several channels. Some channels are used for data transmission, called the main channel. Some channels are reserved for join requests, and one channel is used for downlink responses from the base station, called the downlink channel. LoRaWAN sensors can operate in 3 modes called Class A, B, and C. Class A is the default operation mode supported by all LoRaWAN devices. Class A sensors are capable of bidirectional communications. It's similar to NB5 DRX mode. The Class A sensors transmit data if needed and can receive data only shortly after transmitting. The second mode is optional and called Class B. While operating in this mode, in addition to Class A features, sensors are capable of scheduled downlink communication. Base stations occasionally transmit a beacon that specifies the schedule, and sensors receive these beacons and listen to the channel at the scheduled time. The third mode is also optional and is called Class C. This mode is similar to mode in NB5 CRX. A Class C sensor can receive downlink frames continuously, except for times when the sensor is busy transmitting. Let's now consider a Class A LoRaWAN sensor. Figure on the slide illustrates its transmission procedure. If the sensor has some data to transmit, it randomly selects one of the main channels and transmits the frame. Note that during the transmission, the frame occupies the whole channel. T1 seconds after the transmission ends, the sensor opens the first receive window. For a short time, the sensor listens to the main channel, waiting for an acknowledgement from the base station. If the sensor receives a downlink frame intended for it, then the sensor does not open any other receive window. Otherwise, the second receive window is opened in the downlink channel, T2 seconds after the uplink transmission. If a preamble is detected during one of the receive window, the sensor does not close that receive window until it demodulates the frame. If the sensor does not receive any of the acknowledgement, similar to NB5, it retransmits the frame after random delay within the retry window shown on the slide. The sensor retransmits the frame until it receives an acknowledgement or exceeds a retry limit. Moving on to the simulation scenario. Let's consider a network with 10,000 sensors uniformly distributed in a 1 kilometer radius circle around the base station. Sensors and a base station are static. NB5, Sigfox, and LoRaWAN have different coverage ranges for each bit rate. However, within the 1 kilometer range, sensors can use any bit rate in any technology. The LoRaWAN base station allocates two main channels and one downlink channel with 125 kilohertz bandwidths. In NB5 networks, the uplink band is 204.8 kilohertz wide, and the downlink band is 102.4 kilohertz wide. In Sigfox networks, the uplink band is 192 kilohertz. We consider the Okamura-Hata signal propagation model for urban areas. Sensors generate new frames with an exponentially distributed time offset after completing the previous transmission procedure. The frames are received successfully only if the signal to interference and noise ratio for the transmitted frame exceeds the threshold shown on the slide. For Sigfox and NB5 networks, the threshold is equal to 7 decibel. LoRaWAN devices use the LoRa modulation, which requires a much lower signal to interference and noise ratio to successfully receive a frame, which is shown on in the table 2. Let us consider the following three scenarios. In the first scenario, the unreliable transmission of short packet scenario, the payload size for all frames is 8 bytes. NB5 and LoRaWAN sensors transmit frames in the unacknowledged mode. Sigfox sensors transmit each frame only once. In the second scenario, the unreliable transmission of long packet scenario, the payload is generated in portions of 48 bytes, which means that LoRaWAN sensors transmit data in a single frame, while NB5 and Sigfox sensors operate using block transmission. In order to transmit 48 bytes of payload, NB5 sensors that can transmit up to 8 bytes of payload in a single frame generate 6 frames, while Sigfox sensors that can transmit up to 12 bytes in a single frame generate 4 frames. In the third scenario, the reliable transmission of short packet scenario, the payload size is 8 bytes. However, LoRaWAN and NB5 sensors operate in the Class A and DRX modes respectively, and all of the transmissions are acknowledged. Sigfox sensors operate in the multiple frames U procedure, which means that they transmit each frame 3 times. For the described scenario, in this research, we state the problem to compare NB5, Sigfox, and LoRaWAN networks in terms of packet loss rate, packet error rate, and the average delay, and to determine which technology is the most reliable in each scenario. Let's now proceed to numerical results. Starting with the unreliable transmission of a short packet scenario. For Sigfox and NB5, we consider a scenario where all the sensors in the network use the same bitrate. While in LoRaWAN network, each sensor is allocated one spreading factor during its initialization with a probability which is inversely proportional to the duration of a frame transmitted with this spreading factor. Such allocation ensures a low packet error rate that is uniformly distributed among the spreading factors. Figure on the slide shows the dependence of packet loss rate, PLR, and the packet error rate, PER, on the rate. Rate is the ratio of the total number of generated packets during the simulation to the simulation time. In this scenario, PLR coincides with PER because frames are transmitted without repetitions or retries and can be lost only due to collisions with other frames. As we can see in the Sigfox network, PLR and PER are lower than in NB5 and LoRaWAN for all rates because of different amounts of control information added in each frame in these technologies. Specifically, to transmit a 64 bits payload, Sigfox sensors transmit 157 bits. LoRaWAN sensors transmit 204 bits, and NB5 sensors transmit 256 bits. Therefore, Sigfox frames have the lowest overhead, which means that a frame transmission in Sigfox network takes up fewer time frequency resources and thus has a lower probability of collision than in NB5 and LoRaWAN networks. Note that even though the overhead in LoRaWAN frames is lower than in NB5 frames, PLR and PER in these networks are almost the same because LoRaWAN and NB5 use different modulations. As was previously described, LoRaWAN sensors use LoRa modulation and NB5 sensors use DBPSK. On the one hand, LoRaWAN frames occupy the entire channel during the transmission, while multiple NB5 frames can be transmitted simultaneously without collisions. On the other hand, LoRaWAN frames have lower overhead, and if transmitted with different spreading factors, the frames can be received and decoded simultaneously. Such differences lead to similar values of PLR and PER in LoRaWAN and NB5 networks. Let's now turn to the unreliable transmission of long packet scenario. The figure on the slide shows the dependence of PLR on the rate. As we can see, the LoRaWAN network achieves the lowest PLR because of the lowest overhead. To transmit 48 bytes of payload, LoRaWAN sensors have to transmit only one frame, while Sigfox and NB5 sensors have to transmit 4 and 6 frames, respectively. Sigfox and NB5 sensors transmit frames in a block with a random delay between frames, which reduces the probability of collision. However, the PLR for block transmissions is much higher than the PLR for single frame transmissions because of higher overhead and because loss of a single frame leads to the loss of an entire packet. Thus, LoRaWAN is more reliable compared to Sigfox and NB5 for transmitting long packets. Now we'll move on to the dependence of PER on the rate for this scenario. Even though the LoRaWAN network achieves the lowest PLR, its PER is higher than in Sigfox. Since LoRaWAN sensors transmit only one frame without acknowledgements, PLR and PER for LoRaWAN coincide. At the same time, in NB5 and Sigfox networks, packet error rate demonstrates how many frames in a block are received unsuccessfully, compared to packet loss rate, demonstrating the loss rate of the entire block transmission. Therefore, PER is lower than PLR for NB5 and Sigfox. NB5 networks demonstrate the highest PER due to the biggest overhead. Let's turn back to the PLR plot. As we can see, the figure shows the PLR values up to some maximum rate value. And this maximal rate value depends on the technology and the bit rate. For example, the 100 bps Sigfox curve stops at approximately 40 packets per second. As was mentioned before, we consider the traffic model where sensors generate new frames only after the transmission of the previous ones is finished. And thus, at some rate, the network reaches saturation and cannot achieve higher rates, because generation time of new frames is negligible compared with frame durations and interframe intervals. NB5 networks operating using 50 and 400 bits per second and Sigfox networks demonstrate the lowest maximal rate because the total duration of block transmission is much longer than the frame duration. Such a high ratio is the result of randomizing time interval TP between consecutive uplink frames. Because in this scenario, T start equals 10 milliseconds and T end equals 100 times the duration of the frame. Moreover, such randomization does not only lower the maximum achievable rate, but also has a significant effect on the average delay. Let's have a look at the dependency of the average delay. Bar plot on the slide shows the average delay for different scenarios. Since there are no acknowledgements, average delay does not depend on the rate. Figure A shows the average delay for the unreliable transmission of short packet scenario. Here, the average delay just equals the frame duration. The average delay for the unreliable transmission of long packet scenario with the randomization is shown on the figure B and is significantly higher than for the same scenario but without the randomization, which is shown on the figure C. For example, NB5 operating at 50 bits per second demonstrates an average delay of almost 25 minutes, meaning a 40-time increase compared to the same scenario without the randomization. Without the randomization, and 250 increase compared to the first scenario. However, even with the randomization, NB5 network operating with 25,600 bits per second demonstrates an average delay comparable with LoRaWAN network due to a much lower frame duration. Given that the initial research showed that such randomization does not affect PLR significantly, but notably lowers the maximal rate and significantly increases the average delay, such randomization is unnecessary. Therefore, in the next scenario, to consider a wider range of rates and to lower the average delay, we do not consider any randomization of interframe intervals. Moving on now to the reliable transmission of short packet scenario. Figure on the slide shows the dependence of the PLR on the rate. For rates below 100 packets per second, NB5 sensors demonstrate the NB5 networks demonstrate the lowest PLR because the duration of the receive window and time interval from which the random backoff is drawn if no ACK was received in NB5 are much longer than the frame duration. And since new packets are not generated until the sensor has finished the previous transmission procedure, the base station has a lot of time to transmit acknowledgement, and the channel is not overloaded with unnecessary retransmission. On the other hand, in LoRaWAN networks, the durations of the receive and retry windows are close to the durations of the frame, which results in redundant retransmissions, overloading the channel, and consequently higher PLR. At the same time, Sigfox sensors operate according to multiple frames uplink procedure, which means that they transmit every frame 3 times with the same payload. This procedure ensures reliability, however, it does not perform as well as acknowledgement mode and demonstrates a higher PLR. Note that at higher rates, NB5 networks that use 3200 or 25,600 BPS demonstrate higher PLR than Sigfox because of the high probability of overlap in frequency. Let's have a look now at the dependency of PLR on the rate for the reliable transmission of short packet scenario. PLR in the LoRaWAN network is the highest compared to other considered networks for the same reason as the PLR is the highest one. Sigfox and NB5 networks demonstrate a similar PLR at lower rates because of the similar channel access procedure and the same modulation in these technologies. At some rates, at lower rates, PLR is primarily determined by the probability of success during the first transmission attempt, which depends on the probability of frames overlapping both in frequency and time. Since in the considered scenario, all sensors in Sigfox and NB5 networks use 1 bitrate, this probability does not depend on the chosen bitrate and in our case on the technology, because frame duration is inversely proportional to the frequency band, to the occupied frequency band. However, at higher rates, NB5 demonstrates a higher PLR than Sigfox because of the frequency selection algorithm used in NB5 for downlink transmission. Since for downlink transmission, the server calculates the central frequency as a function of bitrate and modem ID, which means a high probability that the server chooses the same central frequencies for multiple sensors. Thus, acknowledgement transmission is delayed, and if this delay exceeds the ACK timeout duration, then the ACK frame is not transmitted. On the other hand, in Sigfox networks, frames are not acknowledged, therefore resulting in lower PLR at higher rates. Moving on to the average delay. Figure on the slides show the average delay for the reliable transmission of short packet scenario. Since Sigfox network operates without any acknowledgements, the average delay is constant for any rate and equals 3 times the duration of the frame plus 2 times the interframe interval. In NB-PHY and LoRaWAN networks, at lower rates, the average delay is primarily determined by the round-trip time, which is inversely proportional to the bit rate. When the rate increases, so does the number of retries required for the successful frame transmission, which significantly increases the average delay. In LoRaWAN networks, the average delay starts increasing more rapidly and at lower rates compared to NB-PHY. Because of the inefficient collision resolution approach. However, the increase rate significantly lowers at approximately 200 packets per second, which correlates with the PLR reaching a plateau at the same rates. In NB-PHY networks operating at 3200 and 25,600 bits per second, the average delay decreases after reaching the maximum value, because at high rates, the PLR is very high, and frames are either lost and do not affect the average delay, or are transmitted successfully without many retries. To conclude, even though the considered technologies have similarities, such as, for example, channel access in NB-PHY and Sigfox, and acknowledgement mode in NB-PHY and LoRaWAN, the technologies perform best in different scenarios. Sigfox is the most reliable in the scenario where only short packets are transmitted in an unreliable way. Similar scenario is used in the case of collecting data on a daily basis, where the goal is to have relevant data, but not necessarily the most recent. LoRaWAN performs better if only long packets are transmitted in the network, and NB-PHY is more suitable if short packets have to be transmitted in the most reliable way. This scenario is relevant in case of collecting data from sensors, when it is important to get as much information as possible from each sensor, or in case of sending notifications the most reliable way. That is all I have for today. If you have any questions, I'm happy to answer them now.
Thank you, Polina, for your presentation. One question from my side, several questions, in fact, from my side. The first question is about the results. Are they achieved using some simulation or analytical modeling or something else like test bed or something?
Oh, yes, I forgot to mention, yes, we have obtained the results using the simulation. We have developed a discrete event simulator, which implements the described scenarios.
Thank you. And the second question is about the slide number 18 with the description of scenarios. Could you please go on that slide?
18. Okay.
Yes, exactly. My question about the required bandwidth for operation of different networks. Am I understood right that the Sigfox requires almost twice lower bandwidth to operate compared to, for example, LoRaWAN? And do you take it into account in your results?
Sigfox specification defines the only value for operating bandwidth. It can only be 192 kilohertz according to the specification, while NB-PHY and LoRaWAN allow the bandwidth to be configured by the operator. LoRaWAN allows different channel bandwidth, for example, 125 kilohertz, 250 kilohertz, or 500 kilohertz. And it also allows the operator to divide the spectrum into several channels. NBFI specification defines a formula to calculate the bandwidth, and there is some room for operator to configure. We have tried in our simulation to change the bandwidth for Sigfox and NBFI to be the same as in LoRaWAN, meaning 250 kilohertz in Sigfox and NBFI networks, and it did not affect the results significantly. Therefore, we have decided to configure the bandwidth as it is defined in the specification, because it's how it would operate in the real life, and it does not affect the results, even with the different bandwidths in these networks.
Thank you, but I mean, in fact, I mean maybe parallel work of Sigfox, for example, several channels. For example, if the operator have 600 of kilohertz bandwidth, it may use three Sigfox networks in parallel and two NBFI networks in parallel. So maybe it will be more fair comparison if you take this into account. Yes, that different networks use different bandwidth. But in current study, you assume that only a single network is operating. Thank you. I understand. We have one question in the chat window.
Okay, slide 5. Okay, the question is, could you please explain once more why in other works comparisons of LPWAN technologies are inapplicable? What is different in your scenarios that allows you to compare the technologies properly? Well, for example, the works 1 and 2 that compare all three technologies. They just compare the technologies by their nominal parameters, meaning that they just list the properties given by the specifications, and compare them by these parameters. These parameters allows the readers to calculate the file layer nominal throughput for point-to-point connections. However, it does not allow to calculate the throughput in the upper layers, because the throughput in the upper layers depends on many different factors, and this is what we did. We set up a simulation, and we simulated the work of these networks. We simulated the collision, the overhead, and all of that, and that allows us to calculate the actual throughput at the MAC layer. Okay, one more question. What does stochastic geometry correspond to? Does it apply to the whole system or physical layer only? If I remember correctly, in that work with the use of stochastic geometry, the author describes the time frequency interference, and they found the throughput for Sigfox and LoRaWAN networks with their model. However, that that work, the results of that work is not applicable to our research, because they described only the case where all frames have the same duration and width in the frequency domain, so it cannot be used for NBFI. Because there are different occupied bandwidths and time durations. Okay, thank you for the question. Are there any more questions?
Yeah, actually, I'd like to ask one. Thank you, Polina, for your presentation. And could you please maybe scroll to the conclusions while I'll explain. So as far as I like remembered from your presentation, so in your conclusions, you say that, well, different technologies are best for different scenarios. And for example, Sigfox is reliable in unacknowledged unreliable mode, and NBFI is reliable in acknowledged and reliable mode. And if we would like to design some system, I suppose we would like to have some okay, we set up a threshold for reliability and say, okay, what is the capacity of, what is the best capacity we can achieve in this scenario with this requirement on the reliability? So now the question is, can we compare different technologies in such a, I don't know, in such a way?
Well, we did not calculate the other parameters except for the ones that I've shown you, but using our results, anyone who wants to set up a network, if they want to achieve a certain reliability, they can look at the plots and see like at which rate they will be able to achieve the required reliability. And depending on their on the number of the devices they want to set up in the network, they could calculate the desired results, I think.
Yeah, okay, thank you. And another maybe small question is that you considered only a single modulation coding scheme for LoRaWAN, and maybe I missed the reason why did you do so? Because it has more than one, yeah?
Well, there is another modulation, but as far as I know, LoRaWAN networks mostly operate using the LoRa modulation, and the other modulation is used to achieve higher bit rates, and they're mostly used, as far as I know, in the networks with large bandwidth, only 500 kilohertz. And this is why we considered only the LoRa modulation, because it's just more widely used, and because we want to compare the networks in the similar scenarios, meaning that we want to use similar bandwidths.
Okay, thank you. Maybe I misformulated the question. Why did you consider a single bit rate for LoRaWAN?
No, okay, I understand your question. Thank you for your question. I will just scroll down. We consider the LoRaWAN sensors to be allocated one spreading factor, but different devices can be allocated a different spreading factor. And for each device, the probability that it will be allocated for example, spreading factor 7 will be inversely proportional to the duration of the frame transmitted with this spreading factor. So in the LoRaWAN network, different sensors, different groups of sensors use different spreading factors, and we get the average result in the end. Because different spreading factors can be transmitted, received, and decoded simultaneously, so we just average them out.
Okay. Thank you for this. I must have missed this. Thank you.
Thank you for the question.
Could you please go to slide 26?
Okay. Okay.
And the question from Maxim Susloparov is which values of the rate are more typical in practical use and hence more valuable to consider? There is no clear winner on this figure, so I am curious which technology stands out more.
Mm-hmm. Thank you for your question. Well, I would say that okay, let's consider first, for example, the rate 100 packets per second. This is the rate which can be achieved in a sensor network. It's 100 packets per second for the whole network of 10,000 devices means that on average one sensor generates 1 frame per 2 minutes, like that. This rate can be achieved in a sensor network, but I would not say that this is a typical this is a typical traffic rate in the sensor network. So I would have to say that typical rates would be more likely on the left side of the picture. However, as we can see for the more typical rates, the PLR is very small for all 3 networks, but if somebody would want to set up a network to operate at like 10 packets per second for the whole network, they would see which one is more reliable.
I have also several questions. Could you please go to slide 19 with the description of scenarios?
Mm-hmm.
Yeah, this one. Am I understood right that in long packet scenario, the packet size is 48 bytes multiplied by some number, or it have some uniform distribution? For example, can it be 49 bytes?
Thank you for your question. In our simulation, we did not consider different sizes of long packets. It was a fixed size of 48 bytes because with this payload, Sigfox has to transmit 4 frames with maxed out payload size, and NB5 has to transmit 6 frames. But of course, it can be different. But for example, if it were 49 bytes, NB5 would have to transmit 7 frames and 7 frames with the full payload, because NB5 frames do not allow any flexibility in the matter of frame size. But Sigfox networks, Sigfox packets, Sigfox payload can have different sizes in one frame, one Sigfox frame can be transmitted with, for example, like only 1 byte of payload. So it seemed more fair to compare the technologies in this way.
Okay, thank you. I understood. And I guess the last question from my side. I'm not the specialist about the sensor network, but I knew the Wi-Fi standard, and in the Wi-Fi standard there are several ways to increase the performance of the Wi-Fi. For example, RTS, CTS mechanisms, some aggregations, and so on. Are there any performance improvement features which are described in the LoRa or NB5 technologies which can improve the performance? Like, are there any fields for optimization?
Okay, thank you for your question. There aren't a lot of available optimizations because LPWAN technologies are mostly quite simple, because the devices, the LPWAN devices, they're simple and cheap. But there are some features, there is some room for improvement and for some optimization. For example, in NB5 standard, NB5 specification defines a block transmission, meaning that the fragmentation occurs in NB5 technology. The fragmentation may occur on the MAC layer, and it defines the special transmission procedure, and the sensors which use this block transmission, they can choose, for example, they can choose like how many frames in the block they transmit, and other parameters that can be configured. This is one example. However, I should note that in this research, we did not consider the block transmission that is defined in the specification. That is the topic of our future research. Here, we considered that NB5 sensors transmit just frames in a pack, like as the fragmentation occurred on the upper layers. I should clarify that because I may have confused you. But there are some optimizations, but not many, to be honest.
Okay, thank you. So I guess that's all for today. Thank you, Polina, for the interesting talk. I also want to thank all the participants for the questions and discussions. See you at the next seminar. Goodbye.
Thank you. Goodbye.